measured in lab, and in order to do that we do calorimetry. We're hot in the middle of that in third period. We'll wrap that up today. That's where we are right now. Anything y'all want to sort of touch on before we go down the other side of the chart? You guys okay? Okay, so then guys, running down the right-hand side of the chart. Today what we're going to do is we're going to talk about something called Hess's Law. And guys, what you're going to see on the AP test is they will actually force you into the way that you think about Hess's Law. And guys, I will define this for you in just a minute. But when you see the Hess's Law questions in homework and on the test and on the AP test, they are going to pigeonhole you in terms of how you're going to answer the question. Sometimes, given the data that you're given, you will have to solve this through what we call manipulation. Sometimes they will give you other sets of data and you will solve this through what we call computation. So you need to be good at both so that when the AP authors have you do one or the other, you're ready to go. But guys, before we talk about this, we got to climb back up here and we got to talk again. So let's have this foundational conversation. What are we trying to accomplish? We're trying to figure out where these enthalpy changes, how we know what these enthalpy changes are. But guys, oh shoot. What did I do? I touched something. Don't touch, apparently. I'm getting rid of that. Why is my printer open? Doesn't even look like my printer. All right, here we go. So guys, fundamentally, we need to have this question. Where's the energy come from in the first place? When chemical reactions, we're going to talk about how we quantify it, because you got to understand this. Where does the energy come from when an exothermic reaction takes place? You got to know. Say it again. The formation of bonds. Guys, if you don't understand that, seriously, get a tattoo on the back. When bonds form, energy is released. Guys, this is one of the few things you can count on in this class to always be true. When energy is released, bonds are being formed. Now, conversely, what has to happen for bonds to be broken? Energy has to go in. Guys, can you really grab a hold of that? Because it's critical, especially to the idea of computational Hess's Law. Bonds are broken, energy goes in, bonds are formed, energy out. Can I get an amen? I forgot we have a different way of saying it. Josh, it's good to have you back. We should check. Do you concur? Josh concurs. Consequently, oh shit, stop touching. Consequently, we're okay. We're recording this. This is awesome. All right. So guys, here then is how we're going to proceed. We are going to define Hess's Law. Then we're going to explore Hess's Law through manipulation. Then we're going to explore Hess's Law through computation. And then we're going to be done for the day. You guys good to go? Here we go. So guys, first of all, Hess's Law, touching things in a nutshell, it says this. Whether you write this down or not, I think, well, it's always up to you. But guys, this is not a definition that you need to have. You don't need to regurgitate this on the test. You got to understand the idea. So guys, Hess's Law says this. If a reaction can be broken down into a series of steps, the sum of the enthalpy changes for those steps will equal the enthalpy change of the complete reaction. So again, guys, if a reaction can be broken down into a series of steps, and you guys all know mathematically sum simply means to add up. The sum of the energy changes of the steps add up to the energy change of the overall reaction. So guys, I think some of you are grasping this idea, but for some of you it's a little bit abstract. So what I want to do is I want to give you a concrete and yet unrelated example of what this means. You guys ready to go? Don't write this down, but this is the idea. So Let me introduce you to a friend, and actually her name is Haley. This is actually true. So guys, Haley is actually one of my daughter's very best friends. They go to church together, they spend a lot of time together, but guys, you know this about my church, it's not like a ward where you go to church with everybody that's in your neighborhood and you're just always, guys, my church literally draws people from South Jordan all the way down to Santa Quin. Like, our footprint of our church is all of Utah County. And so as a result, this girl Haley, who's my daughter's friend, actually lives up in Lehigh, lives up on Point of the Mountain. So guys, this is Haley's house. North is up, and this is Haley's house up in the Lehigh area. So this is what Haley's life looks like every Sunday morning. So we're going to do this. This is Lehigh. This is Spanish Fork. And this is actually Provo. And so guys, so we got Spanish Fork, Provo. This is Linden. And then this is Lehigh. And so what happens is every morning Haley gets up, and it turns out that they have another friend that actually lives down in Spanish Fork. So what Haley does is she drives 30 miles all the way down to Spanish Fork to pick up this girl named Callista. Then what they do is they drive back up to Provo, and they stop in Provo for coffee. This is about a 10-mile drive. Well, guys, it turns out that yesterday or last Sunday, Callista forgot some stuff, so they had to drive back down to Spanish Fork in order for her to get her stuff. And then finally, once Callista was all ready, they drove to Linden, and they came and picked up Jessica, and then they drove down to Orem, which is where our church is. So guys, how far did Haley drive? Well, this is 30 miles. This is 10 miles. The difference from Spanish Fork to Linden is about 10 miles. And then this is 10 miles. So guys, how far did Haley drive Sunday morning? Well, she went 30 plus 10 twice plus 20. So what is that? 30, 40, 50, 60, 70 miles? Plus the 10, 80 miles. So Haley drove 80 miles Sunday morning. The question is this: when she finally got to church, how far was she from home? She was not 80 miles away from home, right? How far was she? Well, guys, in order to figure out that, we've got to add signs to these numbers. So we need to put another 10 down here because she did those 10 miles twice, and then 20 and then 10. So here's what we're going to say. We're going to say that down is positive. So this is positive 30 miles. But then when she drove back up, we're going to call that a negative 10 because she went in the other direction, and then a positive 10 because she went in the down direction. That puts us back here. Notice she's driven 50 miles, but she's only 20 miles from home. Then, guys, she went all the way back up here, but that's a negative 20 because she's headed in the other direction. And then she drove a positive 10 in order to get back down to church. So, guys, this then is what that means. We've got 30 plus 10 is 40 plus another 10 is 50. But then we've got minus 20 is 30 and minus 10 is 20. And so when this whole nightmare is finally over, Haley was only 20 miles away from home. Do you get the idea? So the idea then is this. The entire journey was 80 miles, but she was only 20 miles away from home. Guys, chemical reactions work exactly the same way. But instead of us talking about north and south, what we talk about is energy in, which is endothermic. Does that break or form bonds? Oh, you missed the transition, y'all. So guys, when we talk about this with chemical reactions, instead of talking about north and south, we talk about in and out. So if energy is going in, does that break or form bonds? That breaks bonds. And if energy is coming out, that's when bonds form. But guys, the same logic holds true. If we know the energy that's going in to break bonds and the energy coming out when bonds are formed, we can add all those up and we can figure out the overall energy change. Do you now understand Hess's law? Do you now understand how crazy Haley's life is? Yeah. You'd love this girl. She's amazing. All right, so here we go. All right, so that's gone, and we're back to Hess's law. Are you good on the ideas? Okay, so guys, let's move forward then. So how do we handle this? And we've already talked about this, but guys, we are going to approach this up and down, in and out process two different ways. One is through manipulation, and the other one is through computation, and we're going to do manipulation first. Now guys, here's where this gets ironic. The AP authors will actually manipulate you into using one of these two processes. And you are quickly going to figure out which one they're forcing you to do because you're being manipulated. You're being manipulated to use manipulation. Huh? Some of you are going, wait, I don't know what manipulate means. Do you guys know what manipulate means? It means well, you understand. Okay. You guys good? What was that, Autumn? Oh, who said that? What did you say? Yeah, to force somebody, but it's also to grab and rearrange and force and to reconstruct. Oh, you did? Oh, shoot. Yeah, welcome to American culture. So, guys, we're going to manipulate first. And in order to do this, the best way to learn it is just to show you. So guys, what we're going to do is we are going to figure out the enthalpy change of this process. It says calculate the enthalpy change of the combustion of carbon to carbon monoxide. Calculate the enthalpy change of carbon to carbon monoxide. Now guys, in order to do this, the first thing that we're going to need is we're going to need a balanced equation. And you're going, oh good, I know how to write balanced equations. Well guys, this is actually about to change a little bit. So the first thing that we're going to do, let me make sure I have space. I don't, I'm going to have to write it down below. So guys, the first thing we're going to do is we're going to write a balanced equation. So we are going to take carbon and we are going to turn that into carbon monoxide through the process of combustion. So guys, when we combust something, what are we reacting it with? Oxygen. So oxygen is our other reactant. What's that? There are no other products in this. So it's not the combustion of a hydrocarbon. But now, guys, what we need to do is we need to balance this thing. And normally you would do this. You would go don't do this, but watch. You go one carbon, two oxygens, one oxygen. So you'd put a 2, so you'd put a 2. Yeah? But guys, understand that if you do that, you are no longer able to answer the question. Because the question says, calculate the enthalpy of combustion. Those units are kilojoules per mole. So guys, what we want to know is we want to know how much energy is gained or lost when 1 mole of carbon turns into 1 mole of carbon monoxide. The problem is our equation is not balanced that way because we've got 2 moles of carbon and 2 moles of carbon dioxide. So guys, how do we fix the problem? You're not going to like this. Here's how we fix the problem. We balance the equation with a fraction. Why? Right? So if you're going, wait, how does that work? Well, guys, watch. Don't write this down, but here's how it actually works. It should balance with a 2 and a 2, yeah? But now let's divide everything by 2. 2 divided by 2 is 1, 1 divided by 2 is a half, and 2 divided by 2 is 1. So functionally what you're doing is you're preserving the ratio, but you're balancing this so that the thing that you're studying has a 1 in front of it, because we want to know the amount of energy needed to consume 1 mole of carbon and create 1 mole of carbon monoxide. So you can balance equations with fractions. Yeah, Kylie. Exactly. Yeah. And again, the reason is that it says, what is the enthalpy of combustion? And when we talk about enthalpies of reactions, those are always given in kilojoules per 1 mole. And we want this to balance with the 1 in front of the thing that we're studying. And then all the others are fine. You guys good with that idea? Okay, so then guys, let's do this again. And let's come back. And so we had carbon plus 1/2 O2 yields carbon monoxide. Yeah? So guys, what then are we trying to figure out? And the answer is this. We want to know the delta H. That's our goal. How much energy goes in or comes out when this process takes place? This is then how you're going to be manipulated. Guys, and this is actually a question off of an old AP test. This is what they give you. They actually give you the enthalpies, the heats of reaction, for 2 other reactions. And guys, at this point, what I'm going to do is I'm going to switch to a blank screen, and we're now going to fully solve this together as a model for how to do this. So guys, this is the way that this goes. So clean this off, go over here, do this. And so guys, then it goes like this. So, and this is what I would really encourage you to do with me. So we've got carbon plus 1/2 O2 yields carbon monoxide. And then guys, we're given these equations. We've got, and I'm going to switch colors. We've got carbon plus O2 yields CO2, and the delta H for that is negative 393.5 kilojoules per mole. Then guys, we've got carbon monoxide plus 1/2 O2, and that yields carbon dioxide. And the delta H for that is negative 283.0 kilojoules per mole. Yeah, no, we can. I know, yes, you should. Understand that on the AP test, this is what's given to you. So they would do it right. So it would be wrong. It needs to be per mole. It depends on whether or not it's implied in the question. So if it said, what is the heat exchange, and we're going to talk more about this in lab when it's contextual, but if the question said, how much energy is released when a mole of carbon turns into a mole of carbon monoxide, then you could just say kilojoules. But if it said, what is the enthalpy of, which is this question, then you would need to have the units of moles. Yeah. You guys caught up with me? Okay, so guys, this is what this is going to look like on the AP test. They will give you what we call a subject reaction. Carbon turning into carbon monoxide, the one in blue. Then they will give you some equations, and they'll say, using this information, figure out the delta H for this process. So guys, this then is what we've got to do. Hess's law. We've got to figure out how to manipulate these equations so that it adds up to this equation. And guys, when we manipulate equations, there's 2 things that we can do. We can flip them and we can multiply them. So here's how this goes. So guys, the first thing is this. As you dig into this, here's the process. And I'm going to change colors again. So what you do is you look at the very first thing that you've got in your very first reaction. And you ask yourself this question. Does it match the subject reaction by side and size? Side and size. So guys, first of all, we've got carbon here. Where's carbon in the subject reaction? On the left or the right? It's on the left. So it's on the left here, it's on the left there, so it's on the right side. Now, does it match by size? Well, we've got one there and we've got one there, so we're good to go. Good? Okay, then guys, we go to our next reaction. And now we've got carbon monoxide. Again, side and size. Is it on the right side? It is not. Does it have the right size? It does. There's one and there's one. So guys, the right side, size, the wrong side. So what do? Guys, what we do I'll stop there. Actually, I went a little too far. Guys, what we're going to do is we are going to take this and we're going to flip it over. And I would strongly encourage you to physically do this, especially on the test. So guys, what we're going to do is we're going to flip this over. And we're going to go CO2. I'm going to write that a little bit higher. I'm going to run out of screen. Guys, what we're going to do is we're going to go bring the products over. CO2 now yields CO plus 1/2 O2. Guys, all we did was flip the reaction over. But when we flip the reaction over, what else changes? Say it again. The sign changes. Guys, think about this. Negative, is that endo or exothermic? Negative, endo or exothermic? Exothermic. So guys, if this reaction is exothermic, if we flip the reaction, then the reaction becomes endothermic, and all we have to do is change the sign. Does that make sense, the flipping, switching sign idea? Okay. Now guys, this. Usually on the AP test, they will give you just the right equations that you need, that once you've gone through this flipping and scaling process, things will add up. So here then is what you do. Draw yourself a line and bring everything down. So guys, do this with me. So carbon is a reactant in the first reaction. Oxygen is a reactant in the first reaction. Now guys, this is no longer our reaction. It's now this. So carbon dioxide is also a reactant in our now manipulated equation. So that's all our reactants. Then guys, we've got our products. Up here, we have CO2. And then guys, down here, we have CO. And we have 1/2 O2. See how I just brought everything down? Now guys, simplify. Carbon on the left, no carbon on the right. Oxygen on the left, half an oxygen on the right. So guys, we are going to subtract half an oxygen from both sides. Here it goes away, and here we are left with 1/2 of an oxygen. We're simplifying. Then guys, here we have a carbon dioxide on the left. Oh, look, a carbon dioxide on the right. What a coincidence. Those go away. And then, guys, look at the only product that we're left with. CO, which is the product of our equation. So, guys, look at what we've now got. The only thing that's left is carbon, half of an oxygen, and carbon monoxide, which is this. So guys, this then becomes the magic moment. Because what did we learn about through Hess's law? If these add up to this, and they do, if these add up to this, then their energy changes add up. So guys, what we now need to do is add these up. And you get negative 393.5 plus what is now a positive 283, and that leaves us with negative 110.5 kilojoules per mole. And Maddie, in this case, we would need to put the per mole because the original question said, what is the enthalpy? Yep. So guys, that is the manipulative form of Hess's law. They give you the equations that you need. You just have to figure out how to flip them. So guys, with that said, are you settled enough that I can show you one more thing? Guys, what if this was the case? And I'm going to try to pick a color that really stands out. Guys, what if, and this isn't true, but what if this equation initially balanced with a 2 there? How would that make the manipulation process different? And the answer would be there would need to be a 2 right here. Remember, we balance these by size and side. So guys, if there was a 2 there, here's how we would handle that. We would go, okay, carbon's on the left, so that's good, but there's only 1 and we need 2, so we would double everything in that equation. But then in addition to that, we'd also have to double this, because doubling the amount doubles the energy. And they will have you doing that as well in homework and on the test. So guys, any questions about manipulation? Yeah, Maddie. Yeah. 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 And you can never get them to add up, right? Yeah, they won't do that to you. Yeah, they purposefully pick equations that work out. And the way to make them work out is always flipping and multiplying. Yeah, go ahead, Santiago. Yeah, so that's a really good question. Several years ago, I don't remember the exact year, they had a Hess's law manipulation question, and they actually gave you a whole nother equation that you didn't need. It wasn't that there was one component of it that didn't fit, it's that you didn't need the whole thing, and they expected you to be able to look at that and just disregard the whole thing. Not many kids got that one right. They just got frustrated and quit. But that's the only, they won't give you an equation that has one little nugget in it that you can't deal with. Typically, they give you exactly what you need. Again, a couple of years ago, they threw that little curveball, but normally it's just exactly what you need. Guys, anything else about manipulation? Do you love the logic of this? It's kind of cool, right? Guys, if you like the logic of this, wait until you see what we're about to do. Guys, this is bordering on almost artistic, what we're about to do. So guys, any final questions about manipulation? Okay, then let's switch gears and let's talk about Hess's law via computation. And guys, in order to do this, this is stuff you want to write down. In order to do this, we need what are called enthalpies of formation. Write that down. Enthalpies of formation. And guys, as you write that down, here's what I'd like you to do. I'd like you to try to define what enthalpies of formation are based simply on the words. Write your own definition for what this means. Don't talk to anybody. You define it. Enthalpies of formation are. Take a swing at a definition. Isaac, are you looking it up? Cheater pants. I'm just kidding. Do you take notes on there? Yeah. Nice. Oh, cool. Did you guys get to take a swing at it? Okay, so let's do this corporately. Guys, by looking at these words and by drawing on all the interesting things we know about these words, we are going to do a surprisingly good job coming up with the definition. So guys, when you hear the word enthalpies of, what are the things that start running through your minds? Changes in heat, maybe chemical reactions, positive and negative. Positive is endo or exo. Positive is exo, negative is endo. So guys, we have all of these rich ideas about energy coming and going and things happen. But then the question is this: what thing happening are we now talking about? Formations of what? Guys, what are types of matter that we know that are formed? Well, compounds, right? But compounds are made of elements. Water is made of hydrogen and oxygen. Salt is sodium and chloride. So guys, when we talk about heats of formation, what we're talking about is the change in energy for the reaction that forms 1 mole of a compound from its component elements. Now guys, this has an abbreviation. The abbreviation for heat of formation or enthalpy of formation is delta H naught sub F. Saying that out loud makes you sound really smart. Delta H naught sub F. So let's break it down. You know what delta means, right? Change. What's the H? Enthalpy. And guys, by the way, and you'll find this even as you get into college where professors get more and more nitpicky about details, you will talk about heats of formation when you actually mean enthalpies of formation. Very seldom did I interact with college faculty that actually said enthalpies of formation. We just call it heat of formation. Understand, we really mean enthalpy. What's the difference? How is enthalpy different than heat? In order for it to be called enthalpy, what can't we do? Work, right? So heat, enthalpy, is heat in the absence of work. But for most times, we just, unless you're in a really deep engineering class, we don't worry about the work. So we use heat and enthalpy interchangeably. Now guys, do you know about the little circle dude? That is not a degree symbol. Do you guys know about this? It's actually read not, K-N-O-T. It is read not. And guys, not in chemistry means at standard conditions. You never need to worry about what the standard conditions are. Typically, it's 20 degrees Celsius and 1 atmosphere of pressure. All you need to know is that we have to define the conditions at which these things are true, because at different temperatures and pressures, the values change. But you never have to worry about it, because frankly, they never change. And then guys, finally, what's the little F stand for? Formation. So this is the heat or enthalpy change of formation at standard conditions. So, and again, we already talked about this, because the not symbol, let me go down here so I can click, indicates standard conditions. 25 Celsius, I was even wrong. It's not 20, it's 25. It never changes. Don't worry about it. So it's generally pure substances at 20 Celsius and 1 atmosphere of pressure. You guys good? Okay. So guys, with that said then, turn to page, oh wait, I already have you clear back in the nether regions, right? We're going to actually go to 184 really quickly. Put a finger or a piece of paper back in 1059. And then guys, let's go to page 184. So guys, here we have a table of standard enthalpies of formation. So guys, let me give you a second to look these over. And as you're looking this over, guys, maybe the question should be, what catches your eye? What do you notice? Anything interesting? Yeah, that's interesting, right? Guys, let's talk about that. Santiago made a great observation. He's noticing that the signs are different. What are the vast majority of them? They're negative, right? So, guys, let's talk about what that means. If it's negative, are they endo or exothermic? Exothermic. Where is that energy coming from? The formation of bonds. But now you're going, wait a minute. Guys, think through this, because this is fascinating, but we're not going to be able to talk about it until chapter 19. So, does it make sense to you if I were to lay out the idea that all of these values should be negative? So guys, think about this. What is an enthalpy of formation? It is the energy change when a mole of a compound is formed from its elements. So guys, in order for a mole of compound to form, what do these elements have to do? Bond together. And when they bond together, doesn't that always give off energy? Yeah, every single time. So guys, the troubling thing is, how are some of these positive? What that means is energy is going in total, energy is going in as these compounds form. Now, guys, we're not going to talk about it now. There's a whole nother concept in chapter 19 that you need to understand before we can talk about this. But understand right now, guys, do you understand how positive values right now should be troubling to you? Yeah? We're going to solve the problem later. But guys, what I would like to do is this. I'd like to make sure that you fully understand what this all is talking about. So guys, for example, isn't hydrochloric acid on here? HCl. It's at the very, very top of the second column. So guys, what does this mean when it says HCl and I'm just going to call it negative 92. Negative 92 kilojoules per mole. What does that mean? And guys, the answer is this. When HCl forms, the delta H for this is negative 92 kilojoules per mole. Guys, what's on the other side of the equation? H2 and Cl2, and then we need to balance it with halves. Hydrogen and chlorine are both diatomic. And so guys, fundamentally what that means in that table is this reaction has that energy change associated with it. So guys, all of these values in that, and this is important, all of these values in this table are actually the energies of reactions, with the understanding that the thing in the table is the product, and then the reactants are just the elements that make up the product. Yeah. No, this is universal to Hess's law, because the thing in the tables, what's that? No. Well, so it's always an option to balance with halves, but we only do it when we have to. And that's the case where, for example, this says the delta H of HCl, and it's understood to be 1 mole. What was funny? I missed it.
You said halves, and then you have to.
That's not funny.
You only use halves when you have to.
Still not funny. Are we really that desperate? Shoot. I know, but it was... All right.
That was like one of the other computer reviews jokes.
I could never use that. The setup is all... I know, I can't. That was not... All right. You guys get the idea? All right. So now, guys, it's time to drink deeply of an idea, and then we're going to get to work. And guys, the idea is this. So that table in the book is obviously not exhaustive. But guys, even if you had a table that did give the delta H's for all compounds, the compound that you will not see in the table are the diatomics. Guys, the diatomic molecules, of which you know there are 7, they are understood to have heats of formation of 0. That means that energy is not given off, nor is energy taken in when iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen form diatomic molecules. You're going to find out in a minute, this makes our lives a whole lot easier. You guys okay? Okay, so guys, check this out. When I discovered, it's like I made this up. When I discovered what I'm about to show you, it was actually one of probably the coolest days in my career, which sounds weird. But guys, I used to really struggle with how to teach Hess's law. How do I help my kids understand the difference between manipulation and computation? You know me well enough to know that when I teach this material to you, I don't ask you to memorize things. I want you to understand what's going on. And guys, do you feel like you understand manipulation? The hard part was teaching computation in a way that made sense. the way that you understood and you weren't just memorizing it. But then, guys, I got into this one year with a group of students, and I was like, oh, shoot, that's really cool. Because, guys, it turns out that computation and manipulation are actually exactly the same process. Let me show you. So, guys, write this down with me. 2HCl, write it big. Do you need to skip down? No, you don't really need to skip down. Write it big. And actually, you know what? I'm going to freeze this and move it up in my slides. Just a bit. That'll work. Yeah, I don't like that. Never mind. I'm going to leave it there. This gives me more place to play. Okay. Did you get it down? Okay, so what are we trying to figure out? And guys, the thing that we're trying to figure out is the delta H for this reaction. Now, whether that, let's say that delta H is negative, exothermic. Guys, make sure you're clear on this. Where does the energy come from if this thing's exothermic? The formation of bonds. Now let's be more specific. The formation of bonds in what? Yeah, the products. The calcium chloride in the water. Can you hang on to that for a second? Now, guys, this. What if this reaction were endothermic? Where is the energy going if it's going in? Energy in does what to bonds? Breaks them apart. But guys, we're not breaking apart the calcium chloride in the water. What are we breaking apart? The reactants. So guys, this gives us two interesting ideas that we can bring together into a Hess's law whole. And it goes like this. In order for this reaction to take place, what has to happen to HCl? In order for this reaction to take place, what has to happen to HCl? It's got to break apart. When that breaks apart, does energy go in or does energy come out? Do this with me. Does energy go in or come out? Energy goes in, so delta H would be positive. Guys, what has to happen to the calcium hydroxide? It has to break apart. Does energy go in or come out? Energy goes in. What has to happen to the calcium chloride? Energy in or out? Energy goes out. And if energy goes out, this is negative. What has to happen to the water? Bonds form, energy out. And this is negative. Now, guys, the question becomes this. Will the overall reaction be negative or positive? Or more importantly, what does it depend upon? So what if the amount of energy going in is greater than the amount of energy coming out? What would the overall reaction be? Positive. What if the energy going out is greater than the energy going in? Then it will be negative. So guys, in order for us to figure this out, all that we need to know is the amount of energy that goes in when these break apart and the amount of energy that comes out when these form, yes? Well, guess what? Guys, all of that information is contained in these four reactions. Do not write this down. Just watch. Guys, what do all four of these reactions have in common? What kind of reactions are they? They're all synthesis reactions. Can we call those formation reactions? Right? Now, guys, look at the products. Look at the reactants. What are all of the reactants? They are all elements. So, guys, what you see in front of you are the synthesis reactions that represent the formation of these four compounds from their component elements. Yes? Where can we find the heats involved in these reactions? What do we call the energy involved in the heats of these reactions? Heats of formation. You making the connection? So guys, this is the idea. These reactions are all the reactions that are the formation reactions of these compounds from their elements. And in order to get the energies for these, we need to look up their heats of formation. So guys, let's do that. Looking on page 184. What is the heat of formation for water? And we're going to go liquid water. What is it? Negative 285.8. And so guys, again, I'm writing this down. You don't need to. This guy is negative 285.8 kilojoules. Okay, now guys, the rest of them, in order to get those, we've got to go back to 1059. All the way to the back. Let me introduce you to Appendix C. You are going to develop a love-hate relationship with Appendix C, and it will mostly be hate. Because, guys, when you need all of these thermodynamic quantities in order to solve the questions from 5 and 19, you got to go back here. So, guys, we need HCl. Oh, we could have got that out of the other, huh? But we can get it back here. Hydrogen. Oh, maybe it's not back here. I'll get that off of one. Where were we at? Is it in the back too, though? Where is it at? What page? Oh, is it under the chlorines? Where is it at? Oh, there it is. Okay, so HCl. And guys, this is aqueous. And then we need the delta H, negative 167.2. Do you see that? So guys, HCl, delta H, negative 167.2 kilojoules. Now, guys, we need calcium hydroxide. Is that under calcium? No, I'll do it for you. So, guys, calcium hydroxide, delta H, negative 986.2. And then, guys, the last one we need is calcium chloride. Is that also under calcium? Negative 795.8. You guys, some of you are writing these down, so I'll slow down with you. But if you're not, you're fine. Tell me when you're ready to continue. Are we okay now? Is that okay? Okay. So guys, don't miss this important idea. This is what this whole idea turns on. So guys, all of these reactions are the formation reactions of the compounds that are in our overall reaction. So guys, I'm going to clean up my mess. So all of these reactions down below are the formation reactions for the compounds that make up our overall reaction. But guys, notice this. Because all of these are formation reactions where the elements are then turning into the compounds, that means that the energies associated with those are heats of formation. Let that soak in. Does that make sense? You okay with the questions there you want to talk about? Yeah, please.
The same energy that comes in to form the compound is the same energy that has to go out to break it.
Dang you. That is exactly, those were the next words out here. You teach. I'm done. Guys, Santiago nailed it on the head. And that's exactly where this is. Okay, this is exactly where this is headed. Nailed it on. You didn't think that one was funny? That one was funnier than the stupid thing you laughed at. Shoot. Okay. He's our humorometer. All right, that's fair. But guys, Santiago, guys, don't miss Santiago's brilliant point. So guys, this represents the energy that goes out when these compounds form. But guys, we understand, this is the pivotal idea, we understand that not all of these compounds are being formed. The products are being formed. What's happening to the reactants? They're breaking apart, but exactly the same amount of energy has to go in to break these apart as is given out when those things form. Yes? Now guys, watch this. We are now going to take off our computation hat and we're going to put on our manipulation hat. Guys, watch. Side and size. Side and size. So, in order to make this work, we look at this first reaction and we say HCl is here, but HCl is there. Do we have a side or a size issue? We have a side issue and a size issue. So let's take care of both. So guys, what's the first thing we've got to do? We've got to flip this over. When we flip this over, what do you know also changes? The sign. And then guys, how do we resolve the size issue? Well, we need two of these, so we double everything. So this becomes a 1 and a 1 and a 2. But what else doubles? The energy. Now guys, watch this. Next one. We've got calcium hydroxide, calcium hydroxide. Do we have a side or a size issue? We got a side issue. So we've got to flip this over. And when we do, we change the sign. You guys good there? Now let's continue. Now we've got calcium chloride. Do we have a side issue or a size issue? Neither. That one's good. Now guys, watch this. We've got water. Do we have a side issue or a size issue? We have a size issue, so we need to multiply this by 2 and 2 and 2. And we also need to multiply this by 2. Now guys, this is where this all comes together, and this is cool. Guys, look at what we've done. We have taken this data, which is heat of formation data, and by using the manipulative processes that we learned studying Hess's law, we have now manipulated these so that they now add up to the overall reaction. And guys, we're not going to do it. You're just going to have to trust me. If we brought all this down, it would in fact add up. But guys, check this out, because we can summarize. And when we summarize, we just discovered a process. So guys, let me ask you a question. What did we do to these first two reactions? What did we do to these? Flip them over. Why? Why did we flip them over? Okay, because they're endothermic. But guys, think about it like this. The reason that we flip these over is these are reactions that represent formation, but reactants are not formed, they're consumed. So we need to turn formation reactions into consumption reactions because the reactants are not formed, they're consumed. Does that make sense? Now guys, what about this? Why did we multiply these by 2? Because those are the coefficients in the balanced equation. Let me now summarize. Don't miss this. Guys, in order to do this math, here's what we did. We changed the signs for the reactants. Why? Because reactants are consumed and not created. Then we multiplied by the coefficients from the balanced equation. Again, and you guys, you're welcome to write this down, but you don't need to. We did two things. We took the heats of formation, we changed the signs on the reactants because they're consumed and not created, and then we multiplied by 2 because those are the coefficients from the balanced equations. Does that make sense? Because guys, guess what? That's exactly what this says. Write this down. Delta H naught subreaction is equal to sigma n times delta H naught formation of products minus the sum of n times the heats of formation of the reactants. This is straight off of your AP equation sheet. Did you all get it written down? You okay? So guys, here's the problem. You are probably not far enough in your mathematical career where you can look at something like this and it means anything more than a jumble of symbols. And that's fine. And it's frankly actually one of the things that makes it so hard to learn from university professors. Because especially in the physical sciences, university professors, math is a language that they are fluent in and their students aren't. And they throw these equations up on the board, and as they're writing down symbols and signs, this rich understanding of what these things mean in the same way that we have rich understandings when we write sentences is going up on the screen or the board. But guys, to their audience, they're going, this is a foreign language. Well, guys, let's go back and let's translate. And it goes like this. This is going to be a mess, but it goes like this. I know there's no context to this, but it brings us back to the idea. So guys, what we did is we started with heats of formations. Where do you find that in the equation up in the screen? Well, that's this and this. That says we need heats of formations. But then, guys, look at what we did. Why did we change the signs of these? Because they are reactants that are not being formed, they're being destroyed. Where is that represented in this equation? The subtraction sign. That is why we subtract the heats of formation for the reactants, because the reactants are not created, they're consumed, so subtracting them is mathematically the same as changing their sign. Then guys, what about this? Why did we multiply by these 2's? Where did they were the coefficients from the equations? Guys, that's what these n's are. Those n's are the coefficients from the equations. Now, guys, finally this. What would we then have eventually done with all of these numbers had we actually done the math? What did you learn previously from the manipulation process? Add them all up. Where's add them all up in this? The sigmas. That means add up. So, guys, this equation that you timidly wrote down into your notes represents everything that you understood conceptually before. What it says is this: the enthalpy change for a reaction can be found by looking up the heats of formation of the reactants and the products, multiplying those values by the coefficients from the equation, and then subtracting the heats of formation for the reactants because those are consumed and not created. Guys, that was a significant moment for me when I figured this out live in front of a bunch of students. But guys, this is really cool because all of a sudden you can look at this equation, which looks like a mess of numbers and symbols and subtraction signs and things that look like an E, only they're sexier. And guys, you can look at this and go, wait, I understand the logic behind it. And that's pretty cool. So guys, this is what is called finding heats of formation through computation. Here's what you need to do though. Grab your AP equation sheets. Find it. Do you see it? What's missing? The ends. Yeah, exactly. The ends are missing. Guys, the AP authors assume that you will know to actually multiply by the coefficients, so they don't give it to you. But again, you'll notice that it's right there. Am I the only one that's nerdy enough to think that that's pretty cool? I think that's pretty cool. Guys, questions about this? Okay. Then guys, we're going to solve one. You want to do this with me. It says this. Don't write it down. Don't write this down with me. Just read. It says this. Calculate the standard enthalpy change for the combustion of 1 mole of benzene, which is C6H6, to form carbon dioxide and water. And guys, you could bounce back and forth, and you could go 6 carbons and 1 carbon, so you need a 6. And eventually what you would find is this is the way we balance the equation. 15 halves. Yeah. So what you would have actually ended up with would have been a 2 and a 15 and a 12 and a 6. But the problem is that it's got to be 1 mole of benzene, so you've got to divide everything by 2, and you end up with 15 halves of a mole of oxygen. Oh, yeah. But guys, regardless, what we need to do is we need to solve this, and we're going to do this together. So I'm going to do this on another screen, and you're going to do this with me. Let me write down the equation again so that we have it. So, and guys, you may want to just do this with me. We've got C6H6 plus 15 halves O2 yields 6 CO2s and 3 H2Os. So guys, what does solving this look like? It does not look like less than this. Here's what you do. Do it with me. So we're going to go delta H of the reaction is equal to sigma. I'm going to include the N, H sub naught formation of products, minus the sum of N times the heats of formation of reactants. Then guys, continuing on from there, what we need to now do is create a form of this equation that applies to the reaction that we're studying. Give yourself space. Goes like this. Delta H naught reaction is equal to parentheses. And now we're going to start with the products. And it will be 6 times the heat of formation of CO2 plus 3 times the heat of formation of H2O. Close parentheses, minus the sum of 1 times the heat of formation of C6H6 plus 15 halves times the heat of formation of O2, close parentheses. Anything less than this will get you 0 on the AP test. Now guys, we need data. So now we go delta H naught reaction is equal to 6 times the heat of formation of carbon dioxide. I think it's under carbon, but I don't know that for sure. Oh, there it is. Negative 393.5. So 6 times negative 393.5 kilojoules per mole plus 3 times the heat of formation. We're going to go water. Where did you say water was? Under hydrogen? No? Where was water? Oh, it's over there. Does anyone have it in front of them? Oh, it is? Can you just give me the number, Ethan? Let's go liquid. And by the way, you would never be asked to guess at that. They would tell you which one, gas or liquid. Negative what? 8.3. And that's kilojoules per mole. Then, guys, we need the heat of formation. So this is then minus the heat of formation of benzene. I'm thinking that's probably under carbon. C6H6, right? Yep. That would be 49 kilojoules per mole. And then, guys, you ready for the magic? Plus 0. Because the heat of formation of a polyatomic is understood to be 0. Now, guys, we do the math. So check me on this, but I get, what do we get? 2 significant digits, negative 3,300 kilojoules per mole. And by the way, guys, if you're interested in how the units work out, kilojoules, or I'm sorry, the units on these numbers 6 and 3 are moles. So moles cancels moles, moles cancels moles, 1 mole cancels moles. Then you're left with kilojoules, and then that's per mole of product. So, but guys, I got negative 3,300 kilojoules per mole. Get the idea? These are long. There's 11,000 different places to make mistakes in these calculations. Take your time. Write them out. Move slow. So guys, make sure that you're writing these out well. So guys, any questions then on any of this stuff? Manipulation, computation. You okay? Christian. I found it under carbon on page 1059. Under carbon, there was C6H6 as both a gas and a liquid, and I guess I chose liquid for some reason. Do you see it? So this wraps around. So carbon goes here, but then it goes back up here. Yeah, that's it. You okay? Yeah. Guys, anything? Here then is the challenge. When you get to your freshman year in college, and you understand all of this stuff, thanks to me, and you have friends that have no stinking idea what's going on, and when you then try to teach to them how to solve Hess's law through computation, if you dare, try to link it back to Hess's law by manipulation, and then drop me an email and tell me how it went. Would you do that? I'd love to know. All right, so guys, that's us for today. In summary, this is our homework for next time. We will be grading all of this, and then we will be collecting your Chapter 19 summaries, and then also your test rewrites. I know that feels like a lot, but you have had about a week to do it. So if you've waited, it's a lot. Yeah. No, let's talk about that third period. My brain's not in that space right now. You guys good with second period in lecture? Guys, thank you. Fun stuff. We will work progressively over the year in terms of fine-tuning your sense of humor. I'm hopeful that by the end of the year, you will show drastic progress. And is it Spencer that's the... So really, if we work on Spencer, we all might improve. That's fair. All right, guys, we're going to take a break when the bell rings, and we're going to come back and we're going to put our lab hats on.